All right, so here we are. This is the machine learning security class. We're down to chapter 11, training deep neural networks. Next week there'll be no class because I'll be at the pen testing contest on Saturday. And after that we have a class, and then it's Thanksgiving and so on. So not that many classes left, but we'll cover what we can. This is fascinating stuff. And this is getting into the sort of deep, complicated models, and I don't have hands-on projects for this stuff. I'm not sure how well we can do it in the limited environment of Google Colab. Probably could do some of the simple ones. The stuff we did last week, we've already made that model in Keras in multiple layers right at the beginning. We did it without worrying so much about how it worked. Now we're going to get into the details, which I find very interesting, but it doesn't. I haven't got a hands-on project to go with it. So we made artificial neural networks with just a few layers. But for more complex problems, you actually need a deep artificial neural network with 10 or more layers, and each with hundreds of neurons and therefore hundreds of thousands of connections. And these are, I think, the artificial neural nets that are actually used in things like self-driving cars and real large language models like OpenAI. And they're, of course, beyond what you can, certainly what you can train in the kind of environment we're using, although you can run them in there. And there was someone doing that project last time. It was I made a project where you run several large language models in Google Colab, and you can do that, although my flags no longer work. I have to find a way to make flags that don't change. They're updating those models more often than I thought they were. Anyway, so here's problems with training. There's a problem with vanishing gradients, which we'll talk about quite a bit here, which made this entire field of artificial neural networks almost useless for a while, where you don't get enough information about some of the layers to train them. And yes, A. Koren has a very good question. What's the motivation for it? Humans clearly use very few layers. That's absolutely true. The human brain mostly uses just a few layers to do things, so you could argue that being 10 layers or more deep is probably a departure from synthesizing a human brain and just moving into whatever works. And remember, none of this is very accurate biochemistry. We're not really accurately modeling a human brain. We're just sort of loosely inspired by what we imagine about how a human brain works. And these models have been developed not really to get closer to biology, but just to do whatever it takes. So and I think this is actually an open question of research. Why do you need so many layers? Do you really need so many layers? And what are all those layers doing? There are startups that have announced their funding recently that are just in the business of trying to figure out what the neurons are doing in artificial neural nets and explain them. And this is closely related to the other big problem, which is how do you make a neural net forget something it's learned without having to retrain it all. And if you actually understood what all the neurons were doing, you could do things like that. And there is some rudimentary progress being made on those nets. But these are very good points you're raising, and I think they're areas of open research. All right, anyway, so you might not, as you see, the small gradient, vanishing gradients is a huge problem. Also, a very large network would take an awful lot of training data, and it might be difficult or impossible to get hold of that much training data, and therefore it might be very slow, and you might have a problem overfitting the training set with all these parameters. So those are issues. So we're going to talk about the vanishing gradients problem, which sometimes could be even exploding gradients. We're using pre-trained layers, faster optimizers, and some of these other techniques. So this is the big one. We've talked about the big breakthrough that made neural nets possible is the backward propagation, where you take a subset of data and you use it, a group of 32 instances typically, a mini batch, and you use it to go backwards through the model and say, okay, I now have an output telling me it has like a 90% chance of being a bag. How much did each parameter here contribute to that? Which is close to what we were just talking about. So you can use the chain rule and derivatives to calculate this, assuming local linearity on all these parameters. And so you can find out how much did this weight matter? How much did this weight matter? How much did the weight connecting this neuron to that neuron matter? How about this one to that one, and this and that? But of course, it should be sort of intuitively obvious that what you'll find is the weights right here will have a strong effect on the output, but the weights down here will probably just get sort of diffused and dissipated and not have such a large effect. So that's called vanishing gradients. when you try to calculate how do I improve the accuracy of this, because I'm training and I know the right answer, I want to know how much each weight contributed. Well, I'll end up just training this layer because it has these neurons, these weights have a strong effect on the output. And I won't be really training these layers down here because even a large change in these weights would not have an effect here. So that's the problem with vanishing gradients. The top layers are more important. The lower layers have a small gradient, so you don't actually move them very much as you go in the direction of steepest descent. And so you don't really train the whole model. And that gets close to what A. Coren pointed out. You really need all those layers. And that's the thing. So what you have to do, by the way, it's also possible that the lower layers have larger gradients in these things called recurrent neural networks that are coming up in a later chapter where you have multiple passes through here. But anyway, the general problem is unstable gradients. If these layers are not all equally contributing to the output, then the ones that are of lower weight are not going to get trained. You're going to end up just leaving them stand still as you move them through tiny steps that don't really optimize them. So that's a serious problem. Like I say, this caused neural networks to be abandoned in the early 2000s. But in 2010, progress was made on this. And here's the point. Remember, when you have each neuron takes input from the neurons below it, and then it has an output signal, and then you run that output signal through a function to scale it to whatever you want. And there are different ways to do it. And the most common way to do it, here's one way. If you have this kind of signal, if it's lower than a certain amount, you have 0. If it's higher than that, you have 1. And in between, you have a range. So what happens is it's only going to learn efficiently in this middle range. If you get higher than this, then changing the input doesn't change it anymore. If you get down here, it saturates on either end. So if you hit a saturation region, then that neuron can't learn anymore because there's no longer any gradient to tell you which direction to move it in. So one solution is this Glorod initialization, where you carefully choose the connection weights to initialize them to compensate for this. So you take the fan in and fan out, the number of inputs and number of outputs, and you use that to determine the standard deviation, and you carefully choose a value in the right range so that each layer will equally contribute to the output. There's one way to get a better initialization start that will get you in a range where hopefully linear motions from that point will train every layer. And so it's really pretty much the same thing. 1 or 2 over fan in is the over the average fan is the standard deviation you need for these, and there's various functions here. But hey, initialization is the one we use for the most powerful functions like swish, which we're going to talk about. So dying ReLU, remember ReLU is this one where you, instead of having the original one, you had the Heaviside function. Everything above 0 is 1, everything below 0 is 0, but that has no slopes at all, so you cannot even do gradient descent at all because there is no gradient. So they switched to this one here, which is sort of the rectified one, where you have 0, everything below 0 is 0, but above that you have linear increase. So that's nice. But it does give you nice gradient here, but it has this flat region of 0, and so that causes dying neurons. Neurons that fall below 0 are now dead. Their signal no longer matters, and so you no longer train them at all. So that's what are they there for if you're not going to train them at all? So they made one solution is a leaky ReLU, where on the left-hand side, instead of having anything below 0, put an output of 0, you have a slope here, which you call the leak, and therefore there's some gradient here and some gradient here. Now there is sort of a perhaps not optimal sudden change in gradient here, but in practice that works pretty well. And then of course you have other functions that do the same thing more and more smoothly. There's various mathematical functions that will approximate this and yet be smooth and have a gradient everywhere. And so what you can do is if you use this special function called SELU, then if you have a multi-layer perceptron, it will self-normalize. Each layer's output will tend to a mean of 0 and a standard deviation of 1, so it will automatically scale to the right size to have the same contribution to the output, which sounds good, but it turns out not to be worth much because it only applies under certain conditions which are pretty stringent. The input feature standardized, every input layer's weights must be initialized in a certain way. You must have a plain multi-layer perceptron. If you have any other kind of network architecture, it's not going to work. And you can't use regularization, which we talked about before, by adding either the first or second order sum of all the parameters to the cost function to try to make you to choose lower parameters. If you do that, it doesn't work, or these other ones either. So those turned out to be so stringent that this thing did not become popular. However, these ones became popular based on the Gaussian cumulative distribution function, which is just another smoothly increasing function. And so there, you see, these are other ones that have just a general curvy structure that's low on the low zero and gradually increases above zero. But it turns out these functions, and Swish in particular, these Swishes turned out to be the optimal ones to use. All right, so Hay normalization and Swish. What do you call this? Regularization, or I forget what you call this function. The output function. Let me get the activation function. Okay. All right. That reduces the danger of vanishing and exploding gradients, but remember, you only chose a certain initialization, and therefore after training it might wander from those initialized values and make one layer more effective than another. So even if you start in a region where all the layers are contributing equally, your improvement might go to an area where some layers are no longer contributing. And so to avoid this, you can go to batch normalization, which adds an operation before or after the activation function of each layer to normalize the input. And so you can see it here. When you make it in Keras, you input the data, and before you do the density, you do batch normalization. Between every layer, you do batch normalization. So you carefully adjust the output of each layer to reach a standard size, like mean of 0 and standard deviation of 1, to make sure each layer has an equal chance to contribute to the output. And this apparently greatly improves deeper networks, although they say it doesn't have any real effect on the kind of small networks we've been making with just a few layers. All right. There it is, looking in the other view of it, where you see that the batch normalization here has only a few parameters added to each one. All right. And there are some equations showing how you do the batch normalization. I think just a general idea how it works is fine. It just scales things so that each layer has the same size of output. All right. And so during training, you keep recalculating the batch normalization, and prediction for single instance can't do that. So what you're going to have to do is calculate an exponential average of the mean and standard deviation for the batch normalization during training, and then freeze that after training. That's how you do it in practice. All right, it turns out to be extremely powerful. It makes models converge for up to 14 times faster. However, it does mean there's more calculation for each model. Instead of calculating the inputs and outputs of every neuron, you also have to calculate these batch normalization layers in between. So anyway, that's but it does tend to be quite popular and quite powerful. So now you got to have some hyperparameters to decide how to smooth these things out in case you're overfitting the data. So momentum is a way to smooth the exponential moving averages, and axis controls how many values are used for each batch. And batch normalization has become one of the most used layers in neural networks. People really like it. It really works. So another thing you can do is clip the gradients during backpropagation, so no one gradient can have more than a certain amount of effect on the output. That you just add that here with a clip value. All right. So that was all to deal with the exploding gradients problem. Now, another one is kind of obvious from biology, although it is not so clear that it really works for artificial neural networks, and this is reusing pre-trained layers. From real brain biology, the type I used to do long ago, or used to work in this field, you can probe into a brain and find low-level cells. There are cells in the eye that just are like photons, or are like pixels. They just light up if there's light in this one direction. And then there are cells after that that pick up things like edges and lines, and at a higher level, there's cells that respond to whole faces. And so there's supposedly low-level details done at one layer and higher-level details and more abstract things done at higher layers. And if that's true, then you could do this. You could have a model that's trained on one task, and then you want to apply to it to another task that's similar. You could take some of the low levels and just not retrain them, just leave the weights the way they are, because supposedly these low levels have just learned, if you're taking, say, images, to just detect edges and simple shapes. And therefore, even if this one was trained to tell cats from dogs, and now you want to tell different human faces apart, the lower level activities of those would be the same. So you could save yourself time and money by not retraining the first few layers. That's the idea. And the point is this will speed up learning and it will require less training data. So that's a thing that could happen. So first you try freezing all the reused layers, then you unfreeze one or two of the top hidden layers and see if performance improves. Is the way you could do it. You may need to drop some of the hidden layers. Some of these higher layers may have learned details that are too specific to this task and don't really work for this task, so you'll have to remove that layer. That's all right. And you can train more layers if you have more data, but the main reason you would do this is you don't really have enough data of the task you're trying to learn. And so when is this going to be best? With small, dense networks like the ones we've made, it doesn't work very well because we don't have very many layers, so it's not really true that the low layers are doing something very different than the top layers. All right, it works best with deep convolutional neural networks. So here's what you might do. You might train an unsupervised model on unlabeled data. So you can do this like with an autoencoder that represents the input data. You can do an adversarial network that generates data similar to the training data and learns to discriminate real from fake data. This is one way to make trained data out of untrained data. You could modify the data and then learn to detect that modification, like adding noise to it. This is what Stable Diffusion does. You start with pictures of real Picassos, then you add noise to them, then you train a model to remove noise from a Picasso. Then you feed in completely random noise, and it will remove the noise and turn into a randomly generated thing that looks like a Picasso. So that's what you're doing. That's your generative adversarial network, where you have corrupted data in order to create data with labels. That's what diffusion does. All right. So this technique has become popular. Then there's another technique was used for a while called greedy layer-wise pre-training, where you would train just one layer at a time and then go back and train this layer, freezing each layer. This was because you didn't have the ability to train all the layers at once. Now we have trained the whole model at once, so this is not used that much. All right, and another thing you can do, of course, is pre-train on an auxiliary task. So if you want to do facial recognition, but for, say, the employees at your company, but you only have a few pictures of each individual, you could pre-train on a lot of random pictures from the web. And since you don't have labels to that data, you could take labels like whether you just train on whether they're just pictures of the same person. So you could scrape everybody's Facebook profile and get all the pictures of the same person and do that for like 100,000 people. Now you've got a big set of data. You can train your model on the general task of telling one face from another, and the lower levels of that model will presumably serve for your new one. Or in natural language processing, you can start with a model trained on random web data and then train just the higher levels on the new data you want. And this is essentially what Microsoft Copilot does. I was very pleased to observe this. Well, Microsoft Copilot is Microsoft's commercial product to help your company, and what they do is built into your app like PowerPoint and Word is Copilot, and it will then go to the large language model that Microsoft has that's been trained on the whole internet, and then it will include, with pre-processing, it will include your company data, which is of course much smaller, as like retraining the high levels. And I don't know if they actually do this in a simple, I don't think it's at all as simple as having the low levels trained here and just retraining the high levels, but it's doing something similar in effect. And this is what they pushed a lot, and people have argued about this a lot. And one thing they've found, by the way, is when you retrain to try to add your company data, that tends to erase the security barriers that they put in here. So it's more likely to no longer obey your rules. And it does not completely remove all the bad habits it learned from the world out here. So, this is a work in progress. We're trying to develop these things. But anyway, you can get some version of it from Microsoft. And this is called self-supervised learning, when you automatically generate labels from the data itself. For example, you could take real sentences and then omit one word from each sentence, so you know what the right word is, and then get your model to fill in the word. Or you can do what Stable Diffusion does. You could take an image and then add noise, and then when it tries to remove the noise, you know what the image looks like without noise, so you can see how well it's doing that. All right, let's try a Kahoot. Let me open up another window in the right browser here and get to it. Yeah, I've just updated this browser, and the graphics are fouled up now. You can see. I updated it because there's supposed to be like a large language model in the browser, but as far as I can tell, I didn't get that. But what I did get was the graphics have become real unreliable. So presumably they will improve it. That's why, I'm not... people say you should always put on the updates, but in practice all the updates do is change your old bugs to new bugs. But they do patch some security flaws. Alright. Alright. Alright, switch activation function was unpopular because it required too many conditions. The SELU was the one, which would magically, automatically renormalize each layer, but only under conditions that weren't very common. All right, which one is so powerful it makes your network converge 14 times as fast? And therefore, it became very popular. Batch normalization, where you constantly scale each layer to make sure that the outputs always stay at a reasonable level. All right, which method turns unsupervised learning into supervised learning? Yeah, that's self-supervised learning. That's where you take a bunch of unlabeled instances and you change them in a way so now you know the label. So you can then perform supervised learning. All right. And boot. Okay. All right. So let's go back to the slides, which are here. All right, so we'll talk about faster optimizers. There's 4 ways to speed up training. You choose good initialization values for the weights, you choose a good activation function, batch normalization, or you reuse parts of a pre-trained network. And these are all the ways we just talked about previously, but there's a new way. You could use a faster optimizer. Now, the optimizer we've talked about mostly before is stochastic gradient descent, where you use the backward propagation to determine the gradient, and now you know which direction is causing the error to go down fastest, and you take a step in that direction, and just repeat that over and over. But these are all ways to improve stochastic gradient descent. All right, so here's regular gradient descent. What it does is it takes the theta is the matrix of all the parameters, probably just an array of all the parameters, and it replaces it by subtracting a learning rate step size times the gradient of the cost function against all the parameters. So you find out which direction moves the cost down, and you multiply it by the step size, and you move the gradients by that amount to try to move towards the minimum cost. So that's the obvious way, but what this means is when the slope is gentle, it will take small steps. And when the slope is large, it will take larger steps. So if you have a period of a gentle slope, it might just take tiny steps and not make any significant progress towards the bottom. All right. So the cure here is to add this thing called momentum, and this will include momentum from previous gradients, so the size of your step depends not only on the immediate gradient where you are, but how long the gradient has been pushing you in that direction, so it will pick up speed as it rolls down a gentle slope, the way a real ball would, to try to get somewhere, even if the slope is small. And so beta is the momentum, which is here, and this is the friction, which is typically 0.9. So you divide the step size, take 10% off the step size every time, and then you add in a step size here to add to it. So the idea is it will, the gradient will determine the acceleration instead of the speed. So that's one thing, and it escapes from plateaus faster than stochastic gradient descent. Then there's Nesterov accelerated gradient, which calculates the gradient by looking ahead in the direction of the momentum, which is almost always better, and there's a diagram explaining this. So if I'm here, and my gradient descent is here, then I would take a step in this direction, but I take a step down here, then this is my previous momentum. Now a regular momentum update would then add this to it, having calculated from the same point where to go, but what it's going to do is it's going to calculate the gradient from here, so it's going to follow the shape of the curve. So this is the part of the step carried over from previous momentum, and the new part you calculate from the new point, not from the old point, which kind of is obvious, but it was not included in the original equations. That's Nesterov accelerated gradient, and as you can see, this is much more likely to be moving towards the minimum, you would think. Then there's eta grad, which moves more towards the global optimum instead of just down the steepest slope. And it works, it turns out, for simple quadratic problems, but it tends to stop too early, and it's not recommended. It scales the steps down and stops before reaching the optimum. So that was another option. RMS prop improved eta grad by accumulating only the recent iterations in gradient, and this turned out to be better than eta grad, so it didn't carry too much old information in, causing you to go off course. And this was preferred, but then an even better thing was invented called ADAM. And ADAM is adaptive moment estimation. And this, of course, combines the previous things. That's the way almost all improvement works. You combine the previous ones. You can find momentum optimization, RMS prop, and so it's got momentum, it's got a decay rate, it's got a smoothing term, and it's got a learning rate, and combines them all to calculate what step to make in your gradient descent. Eta max modifies the loss function, but it didn't turn out not to be much of an improvement. And NADAM added the Nesterov trick of calculating part of the motion from the future point instead of the current point, and sometimes is a little bit better. Adam W. added a regularization technique called weight decay, which will lower the weights in each training iteration by a decay factor. All right, and so here's a summary of all these things. Convergent speed of stochastic gradient descent is small, more stars is better. And as you can see, eta grad and Adam W are all much better. Convergence quality is very good of stochastic gradient descent. If you give it enough time, those little steps will eventually find the real minimum, presumably, although you have a problem with local minimums. But eta grad is bad, it stops too early, and the rest of them are all pretty good at converging. They're fast and pretty good at finding the bottom. So now you might want to consider a sparse model, which would be where most parameters are 0. You can do this by applying strong regularization. Remember, you add to the loss function just the sum of all the parameters, all the weights, so this encourages some of the weights to be 0. And the point of that is if you can make a model that fits with most of the weights being 0, then it'll be much faster and easier to use when you're done. You don't have to add so many terms to calculate the result. All right. And then there's an issue of scheduling. You can use a schedule to adjust the learning rate. You might want to change your step size. So if the step size is way too high, then you'll just go in the direction of steepest descent, but jump way too far and end up at a high point and then another high point. And after a while, you're just randomly jumping all over the place. As epochs go by, you're not even improving the loss. Then if your eta is too small, it will slowly move down and take a long time to get there. And as there's one that's just right that will optimize, will load it as quickly as you can. And they say what would be best would be to start with a high learning rate here. So you make rapid steps towards the bottom and then adjust the learning rate to be smaller after you're getting closer to the bottom. That's an adjustable learning rate. So there are schedules. Drop after each step, gradually drop by a factor of 10 every S steps. Use a constant learning rate for a while, then a different learning rate, and so on. Measure the validation error and reduce the learning rate when it stops dropping, which makes some sense. These are just various ways to do it, and as you'd imagine, they all work more or less the same. One cycle scheduling will increase the learning rate by a factor of 10 during the first half of training and then decrease it during the second half, and this turns out to be converged much faster than the other methods. So I guess they're not all exactly the same in how fast they are, but they're all exploiting the same general point. So then you've got overfitting, and so you want regularization. So one technique, of course, is early stopping. We've talked about it before for gradient descent. You watch the loss function. It's going down, down, down. When it starts going up, you quit. You say, well, I appear to have hit the bottom. It's going up now. That's one way to do it. Another way is to add the absolute value of all the weights, which will tend to give you a sparse model, or add the squares of all the weights. And this will work for some of these step controlling functions and not for some of the others. All of these do tend to regularize the model. There's another one which I thought was very charming, dropout regularization. This has turned out to be popular. What you do is at each training step, you just ignore some of the neurons, like they've dropped out, they've broken. And you have a high probability of this, like 10 to 50%. And this, of course, produces a more robust network that generalizes better. And I was amazed to see this. I heard of this years ago. This is called the Chaos Monkey. They use it to just, at Amazon and at other large companies, they have a service running that will automatically shut off some of their servers, some of their cloud servers, because they want to train all their developers and everybody to be ready for when there's an outage of something. So they deliberately cause real outages of real functions during business so that everybody has to learn, don't write anything that depends on a single point of failure. Everything you use has to refer to a group of servers and pick one of them and be able to handle if it fails. So it's the same kind of thing here. And I imagine it's the same in your brain. There was an interesting discussion in your book where they said you wouldn't have a company where you just take some of the employees and 10% of the employees and just send them home every day and tell everybody to do the work for them. That wouldn't work. And they said, well, maybe that would work. In fact, there are companies that do things like that, although not in that fashion. They do things like forced vacations and let someone else take over your role. But in fact, if you did that, you might have a more robust company that could survive problems like people quitting and strikes and stuff better. Anyway, all right, so that's dropout regularization. They say in practice, you only do it to the top layers. So you just choose some of these and drop them and ignore them while training. And then different ones, you ignore them for the next step of training. And in practice, this seems to cause it to follow the trend of the data and not focus on the details of the data. So, all right, there's Monte Carlo dropout, averages many models at different random dropouts. Max norm regularization that forces all the sum of all the squared weights to stay below a maximum, which is similar to the L2 normalization, but not quite the same. All right, and so anyway, there's a summary of the end result here. So if you have a kernel initializer, I use the key initialization, I'm not quite sure what that is. For the activation function, they recommend using ReLU or Swish. For shallow networks like we've been using, ReLU, which is the one that's just flat and has a straight line above 0, and use Swish if you have a deep neural network. For normalization, you don't need any for shallow networks, but you need batch normalization for deep. Early stopping or rate decay for regularization. And for optimizers, they recommend the Nesterov accelerated gradient, or ADAM-W. And for your learner rate scheduling, your performance scheduling or one cycle is just what they recommend from experience. And this was for deep neural networks. For a simple stack of dense layers like we've been doing, then there's another set of recommendations. Nothing terribly exciting there. All right, anyway, those are all the details. And this gets us up to sort of modern times with all the research. So let's try another Kahoot. All right. Good. All right. All right, so which one goes very slowly if the gradient is small? Yeah, the stochastic gradient descent, the normal one, that's the problem. If the gradient is too small, it's going to take too long to reach the bottom. Which method tends to stop too early? That was the ADAGRAD, adaptive gradients. All right. Which method uses weight decay? ADAM-W, all right. All right, which one ignores some of the neurons during training? That's dropout. All right. All right. All right, I'm going to stop this recording.